All right, just like a minute, 1 minute. Okay, that's time. Please turn in what you have. Anybody else? Okay, thank you. Last call. Okay, names on them. Anyone else? Do what? You can talk to me after class. What are you changing? How much are you changing?
I made a mistake on the last part.
I'll find it in there. What does it say? 1 minus what?
X.
Okay. All right. Okay. Let's go over this. Okay? Let's go over this. Because if you have trouble with this, you're going to have trouble with the rest of today and the day after that and the day after that. Okay? So we are trying to take this region right here, and we're trying to wrap it around y equals 3, right? Which is here. So I'm trying to wrap this around this up here. This is my axis of rotation, right? Now, from what I can see, there's a lot of people trying to just use formulas and trying to just plug things into a formula instead of actually like looking visually at what you're doing. And I told you all last time, I think that's the best way to learn this, is to understand what's happening visually. So what I showed you was draw a rectangle, right? And then to the side of this, we're going to redraw everything again. So I'm going to draw my x-axis. Here's my x-axis, right? This is x. Then I have my rectangle. Then I have the curve on top, which is the 2 minus x squared. Then I have the curve on the bottom, which is the x squared. Then I have my axis of rotation, which is up here. I'm going to wrap it around. It's going to create a washer. All right? I need to know the volume of this washer. All right? The volume of that washer, I'm going to need to know, to get that, I'm going to need to know the outer radius and the inner radius. Okay? The distance from the axis of rotation to the outer edge is the R out. That's my R out. The distance from the axis of rotation to here is my R in, right? So now with the nice picture in front of me, not a formula that I'm trying to just cram stuff into, with the picture I can look at what this distance is. Well, I know the distance from here to here is what? 3, right? And I want less than that. I want to take away a little bit. How much? I want to take off that red part, this distance here, which is the x squared function. So the R out, right, this distance from here to here is x squared, right? And I may as well put this here while I'm here. The distance from here to here is the 2 minus x squared, right? So R out is equal to the whole distance 3, take away x squared. The R in is the whole distance 3, take away what? 3 minus 2 minus x squared in parentheses. That negative must distribute. 1 plus x squared. Right? Distribute the negative through. Yeah, the 3 is big, right? Because that changes where you're rotating. If you don't have the 3 incorporated in there, you're rotating around the x-axis. That's what you're doing, which is a totally different volume. Okay, so now once you have R out, R in, now this is where you actually maybe have to remember some sort of formula. And that is, your volume will be pi times the integral. Now we need to figure out where our rectangle moves from. Starts at 0, goes to 1, right? So 0 to 1. And then it's R out, what? Squared minus R in squared dx. Done. If I don't ask me if I had this. If it's not that, it's wrong. I mean, it's got to be that. I'm not asking you to work them out, right? I'm not asking you to work them out. I'm asking you to get the correct formula. That's what I'm asking. Now, maybe on the quiz I'll be a little bit more chill, but on the exam I want it right, you know, because if it's wrong, it's wrong, right? I mean, it's really wrong because we are depending on that answer. That's the way. It's not like a little mechanical. I forgot the 2, you know.
Can you work out the 0 to 1 interval? I know it's you set them equal to each other, right?
It's where the 0. Oh, you mean knowing that that's 1?
Yes.
You would set these equal to one another, but I gave you the graph so you didn't have to do that.
I tried that, but and then I looked at the graph instead.
You set them equal to each other, and
I tried to, but I somehow messed it up.
yeah, I think you overdid it. Just move that to the other side and add it. You get 2 of those. Divide by 2. Square root. Plus or minus 1.
Yeah, you'll be able to see it.
Yeah,
Like
yeah.
X squared equals square root of 1 somehow.
Yeah. Yeah, well, that'd still be.
Yeah.
Yes.
So I did it right. It's just I'm trying to see if I can visualize the property or something. Like
Yeah.
because that's that invisible line wrapping it around, the outer is going to be like kind of going farther away from it.
Farther away from it. Yes.
Kind of trying to think of it like.
Yeah, I think I said in class, I like to envision like if you were standing on that axis of rotation. Like imagine I'm standing on the axis of rotation and the rectangle's out over there on the ground. Right? R out is the distance from me to the outer edge of that rectangle, and then the inner is distance from me to the inner edge. Right? Okay. All right.
X equals 0, is that just the beginning of the interval?
This rectangle I drew was arbitrary, right? It could have been anywhere in that region, right?
But you had the 3 equations, y equals x squared, the next one, then x equals 0.
Yeah.
X equals 0 was...
X equals 0 gave us this bound.
Okay, that's what
Yeah, that's what it gave us this one.
That's what I figured.
Yeah. Because if not, these parabolas go on the other side and cross over and do the same thing over here. And so I didn't want you to deal with that and just gave you that right side of it. 2 times, yeah. You just double it. All right, so I have a different problem for you now. So how about this? What if we have x equals y and x equals y squared? This is going to be our region, and we want to rotate this about the y-axis instead of the x. So what I've given you are not functions of x. These are solved for x, right? So these are functions of y. And so I want to take that region bounded by those 2 curves, and I want to wrap that region around the y-axis instead of the x-axis. So let's draw the picture first.
Also, is this 7.2?
Still 7.2. Yep. So y equals x, or x equals y, that's still the diagonal, right? That's still the diagonal line. This is still this right here. I'll put x equals y. And then x equals y squared is a parabola that opens sideways. And I showed you on your calculators how to use the parametric mode to graph this. but this is a parabola that goes like this, and it goes this way as well. So do you all see the region bounded by the two curves? There's only one region. It's right here. I'm going to take that region. I want to wrap it around the y-axis. So my axis of rotation is here, right, like this. So here's the issue we're going to run into with this. We've been doing rectangles like this, right, vertical, and wrapping around axes that were perpendicular. Like we took a rectangle this way, and we wrapped it around axes that were this way. So our rectangle was always perpendicular to our axis of rotation, wasn't it? Here, if I do a vertical rectangle, right, my axis of rotation would be parallel to it, wouldn't it? Right? If I did vertical rectangles in here, don't draw this, but if I put a rectangle in here like we did before, then if I try and wrap it this way, they're parallel to one another. Washers, the method that I've taught you, only works if your rectangle is perpendicular to your axis of rotation. So I can't use a rectangle that goes vertically. I have to use a rectangle that goes horizontally. But we've done this before when we were doing areas, right? We just change everything over in terms of y instead of x. So if I draw a rectangle in here sideways like this, and now I need to draw, I'm going to go and draw a separate picture again. I'm going to move it over here to the side. Here's my y-axis, right? Here's my rectangle. I'm kind of zooming in on it. I have the blue curve on the right side, right? On the right side, not top and bottom anymore, right side. And then I have the red curve on the left side. My axis of rotation is the y-axis, right? I imagine myself standing on the axis of rotation, and I need to figure out what r out is. So again, it's the distance from me to the outer edge of the rectangle. What would that be? What would that distance, geez, from here to here, this right here is r out. And that would be what? X equals y. So we're doing things here in terms of y, functions of y. So I'm going to put r out is just y. And then r in would be the distance from the axis of rotation to here. That's r in. And in this case, it's just what?
Y squared.
Y squared, right? Y squared. See, these are now functions of y, not x, because we're looking at a rectangle horizontally instead of vertically.
Right.
Does that make sense? Any questions? I have r out, I have r in. I can use the same formula. Now, there is another difference, and that is our rectangle is going to start down at the bottom, move up to the top, right? Go through here. So that means our integral is not going to be, 0 to 1 or something like that on x. It's going to be the y values, isn't it? So I actually need to know, I know that's 0, right? I can just tell. We need to know what that is. Do we know where these hit each other? At what y value they hit each other?
1.
At 1. 0 and 1, right? But you could set these equal to one another, couldn't you? Y, you set the two equal? Let me do it. Where they intersect, you set y equal to y squared. How do you solve that? Subtract, right? Don't divide by y. Subtract. You could go either way. I'm going to put 0 equals y squared minus y. Factor out a y. Two solutions, 0 and 1. Okay? So that's going to give me my limits of integration on my integral. Everything else is the same formula. Pi, right? Integral r out squared minus r in squared. So here it is. I'm going to put it right here. The volume of that will be pi integral from 0 to 1. It'll be the r out, which was y, but then squared, and then minus now the r in, which was y squared, but then squared, and then d y, because I'm doing everything with respect to y.
So this is still a washer, but
It's still a washer, but it's a washer that goes this way. Well, I never drew it, but our washer goes, well, you know what? Yeah, it goes this way instead. So now it looks really more like a washer,
I think I missed a piece somewhere. Why are those squared independently?
That's the formula because when we were determining what the formula of a washer was, It was pi r squared times h. And the radius, for us the radius is the r in, the r out, pi r squared, right? Pi r squared. So we have to take whatever the radius is and square it.
Why isn't it y minus y squared squared?
Because we're looking at that washer as, we're looking at this washer as a big disk minus a small disk.
Right.
Okay? This right here has a radius of r out. So the volume of this is pi r out squared h. This one is pi r in squared h, right? And that's different than pi r out minus r in squared. Those are not the same thing, because this you would actually FOIL out and you would get a middle term which is not included in this.
Right. Well, it's because you're finding the volume for each of those.
Independently and subtracting, yeah. Yes?
For someone who doesn't know what a washer is, what else would you call this method? My little sister doesn't, so she tells her.
Show her a washer and then call it the washer method. Yeah, I don't know what, I mean, every book I've ever looked at has called it the washer method.
Wouldn't you need another set of parentheses and brackets up there that way?
Oh, you mean like around
Yeah.
here? Yeah, I mean, yes, yeah, I mean, yeah.
Just not making triple tests.
Yeah, no, I got, yeah. Most textbooks would not put that there. It's like implied that it's there. I mean, it's, what else could it be, I think, is what most authors look at it as. Like, what else could it be? All right, that makes sense? So basically, everything we've done, we can now do with functions of y wrapping this way. Let's do the same region. Let's go around a different line. So it was x is y squared. This time, that's our region. This time, let's go rotate about x equals, let's go with -2. I'm going to go faster through the drawing, okay? Because we've just drew this region a second ago. We've got this. We had the parabola shape here. We had the linear piece here. This time, though, we're wrapping around x is -2, which is to the left, 1, 2. Our axis of rotation is now there, right? Good?
Yeah.
And so when I go and draw my picture on the side of this, I have my y-axis, I have my rectangle, here's my rectangle. I have my axis of rotation over here. I've got the linear function there. I've got the parabola here, and then I'm wrapping it around, creating this washer this way, right? Do y'all see the big difference? What's the big difference? Yeah, it's bigger, right? The R out's different now, right? Because you're no longer going from this edge to the y-axis, you're actually going from this edge to the y-axis plus this much, right?
Yeah.
And we know how much that is. It's -2 is the actual x-coordinate, but as far as a distance is concerned, it's +2. So you want to look at it like a true distance. So we're going to do this. This right here, from here to here, R out, is going to be what? It's the blue one, which was what?
Y.
Yeah, this blue one here, from here to here, was y. So it's y plus how much more? 2. So I'll just put y plus 2. That's my R out.
That's why it's important.
So you're not treating the rectangle as though it has like distance from the axis. Right?
Yeah, from here to the edge of the rectangle is y,
I see. That is the distance.
right? And then you have to always add 2 to that, because this line was -2, right? Is that all right?
Would it be faster to, so would you say it's usually just faster to graph the graph and then find the
Yeah, sure, if you want to use your calculator for that.
I mean, like, you don't really use your calculator.
I'm saying to graph it.
Oh.
Here to here is y squared, right? Oh, I'm sorry, no, that's not y squared. Accidentally went. I meant to do this piece right here. From here to here is y squared, right? Yes. So the r in, I'm running out of space. This goes up to there. That's r in. What is that for us? 2 plus y squared or y squared plus 2. It doesn't matter which order you put these in, okay? It's addition, so there we go. That's it. You've got your r out, you got your r in. We go to the formula. It's the same limits of integration, right? So the volume of that will be pi integral still from 0 to 1, r out squared minus r in squared dy here. And yes, those parentheses should be there. R out was y plus 2. R in was y. I did that. Yeah, y squared plus 2. This will give you that volume. How y'all feeling? It's okay? Okay. Let's do another one. Same region, different line. Yes?
So with the axis of rotation, how is like -2? So in a sense, like we're just treating it as if like we're just coming back to the x-axis.
Like if we had a measuring tape between you and me, we would count that distance and always consider the distance to be positive. Okay. Is that what you're asking? So we're looking at that distance here as positive 2.
Yeah, so I'm saying, but like if it was like just like it's positive 2 or whatever, then we would subtract that.
Well, yeah, so that's what we're going to do on the next one. I'm going to give you a line over here now.
Okay.
Yeah, and let's see what happens. So let's rotate it around. This time let's rotate it around x equals, I don't know, 4.
So same stuff except.
Same stuff going around x is 4. So I'm going to draw another picture, okay? I'll tell you what I'm not going to do. What I'm not going to do is try and just like say, oh, that means I'm going to add 4. I'm not going to just like guess. I'm just going to add 4 to the functions. Okay, I'm going to draw the picture to make sure I know exactly where things go. So here's my y-axis. Okay, the blue one was the line. The red one was the parabola. Whoa, my region got really small there, sorry. My rectangle, I don't like that. I don't like that. Kind of exaggerate a little bit so I can get a good rectangle in there. Okay, so I have my rectangle this way, and I'm rotating about x equals 4 will be somewhere over here. You could do all your R in, R out over here. You could do it on this. You could, but I always like to just do a separate picture. That's just my personal preference. It's the way I did it when I was a student. So I've got the blue over here. Got the red here. Let's go ahead and just say what those are. That's x, that's y squared. Sorry, that's y squared. The blue one here was y, and I'm rotating it this time around a line over here, right? And I know the distance from the y-axis to here, I know that that's 4, right? Okay, now you're standing on the axis of rotation, and you're looking at your rectangle, and you're trying to figure out what r out is, which is distance from you to the outer edge. That's here to here, that's your r out. I think I've been using uppercase today, but last time I used lowercase for r. It doesn't matter, right? That's r out, and then r in would be the distance from here to here. right? Let's do R out first. I've got to get from here to here, right? From here all the way to here is 4. I don't want that much, right? I want to take what away from 4? This much, which is the y squared. So the R out would be the 4 take away the y squared. Not y squared take away 4, 4 take away y squared.
But what's the difference?
This right here is y squared. This distance is 4. We want that 4 take away this y squared. Take that away from it. This part's being subtracted from the 4. Okay. And then with R in, look at it the same way. You're going, the whole distance would be 4, and you're taking away this much, y, right? Total distance 4, take away the y. 4 minus y. And now I can go to my formula. So the volume will be pi. Integral still 0 to 1 because we're moving this rectangle up and down. From here up to there, we already knew that that was 1. And then it's going to be the R out, 4 minus y squared, that quantity squared. And then minus the R in, which was the 4 minus y, and then that quantity squared dy. There it is.
Would it not be a shell method?
We haven't talked about shells yet. Yeah. Shells are coming in just a minute. Yes?
Just trying to get to my head, like I said, well, it's 4 minus y squared versus like other ones added it. Just trying to solidify that in my head.
I didn't hear a question.
I don't know what I want to ask. I'm sorry, go ahead.
Okay, well, if you can rephrase it in a way that I can answer, let me know.
I'll ask you.
Okay, yes.
So, the one thing I want to understand is, like, in this case, we had it was very obvious that we were going to be horizontal with the x equals. So if you had more ambiguity, what's kind of like the logic there between when you're going to choose the horizontal and the parallels? Because you mentioned it earlier. Like,
Yeah, so like obviously if everything is like y equals a function of x, right? It's solved for y, then you're probably going to want to use vertical rectangles. If it's x equals functions of y, like this, then it's most likely going to be horizontal. But we haven't talked about the next method yet. The next method is going to allow us to adapt and pretty much handle anything. Like not anything, but all, different cases. Just, yeah, hang tight, hang tight. I think we need to see more examples before we can start talking about, like, we don't have the full picture yet. So, yeah.
Sorry.
Nope.
If it was further to the right and it was still wrapped around 4 instead of being close to the origin like that, could you still use this method?
Oh, yeah. Yeah, because it doesn't matter. If this, even if this was like this, like let's say our region looked like this. It was here and I don't know, right here like this. Let's just say that was our region and it didn't go through the origin. I think that's what you're asking me. And we were wrapping around here.
Well, the whole graph was shifted to the right of that line.
Right of what line?
Both functions
Where?
to the right of that line. Yeah.
Oh, that's my next example.
Okay.
Yeah, yeah. I need to give you one like that. We haven't done one like that yet. Yes.
Never mind.
Okay. Okay. So the next one I'm going to show you is kind of a weird scenario, but it can happen. So I need to change the region in order to do this. So let's let our region be this. Y equals sine x plus 2. Let's go with y equals 0, x equals pi, and x equals 2 pi. That's our region. That's our region, okay? And I'm going to rotate this about x equals pi over 2. So let me graph the region first. right? We all know what sine of x looks like, right? And then we're going to just move the whole thing up 2. So if I move it up 1, right? If I move it up 1, then all the bottoms will touch the x-axis, right? If I move it up 2, everything's going to be 1 unit above. So yeah, so here's 1. Let me do it this way. The normal sine function would look like this, right? The normal sine function would look like that. Oh shit, not even close, like this. Okay, that would be your normal sine function, something like that, between -1 and 1. We want to take this whole picture and move it up 2 units, right? 2. So now this point goes up to here, right? This point goes up to there, right? This point goes up to there, and then it comes down, and the lowest it goes is 1, right? Okay. So it's going to go up to 3, back down to 1, and like that. Okay, that's what the graph of sine of x plus 2 is, right? It goes in both directions forever, right? This is actually 2 pi, right? It goes through 1 period in 2 pi. Halfway is pi. Why do I know that? Pre-cal, right? Pre-cal. And then y equals 0 is what?
The x-axis.
X-axis, right? So that's the x-axis. I'm going to label that here. It'll be our blue right here. Okay, this is y equals 0. And then vertical line through pi, right? A region through pi and 2 pi. All right, do you all see the region that is bounded by all 4 of those curves? Yes? Right here. Right there. Right, that's bounded by all 4 of those? Remember, this y-axis is not bounding anything, right? Right. If we use that paint bucket tool, right, that we talked about, if I click it right in here, it's going to flood all this out, right? But if I click it in here, it just fills this region in. Okay, now the one you were asking about, David, time out on that. I'm going to do this one first, then we'll get to